This is experiment number 4 on ammeters and voltmeters, and you'll learn in this lab how voltmeters and ammeters work. Of course, we've used voltmeters and ammeters in the previous lab, but now we'll really begin to see how they operate, and also how you can change an ammeter and voltmeter to fit your particular situation. At the heart of an ammeter and voltmeter is a galvanometer. We've used galvanometers. We used them in the second lab. They consist of a permanent magnet. This is a permanent magnet right here. And then there's also permanent, like the kind you play with as kids that you can move together. But then there's also an electromagnet right here. And an electromagnet, it's a coil of wire. When you run a current through it, it creates a magnetic field. We'll talk about that later in the lecture about how that operates. But in short, when these two magnetic fields interact, they exert a force on this dial, and then that dial will move depending on the amount of current that is running through a galvanometer. So a galvanometer measures current. It's very, very sensitive. And so before, when we used it in that experiment where we had the dipole electric field set up, and then you measured the current between two different positions. So if you're measuring the current between here and here, for example, this resistance is really big. That means that the current is going to be really small, right? Because V is equal to IR. If I have a big resistance, that means I'll have a small current. Galvanometers are very, very sensitive. They measure a very small current. Also, most galvanometers will measure either positive or negative current. That is, they'll measure current in either direction. So you'll see that on your galvanometer, the dial will go this way, and then sometimes the dial will go this way, depending on the direction of the current. That's not true for other measuring devices like the ammeter and the voltmeter. Okay, so in using an ammeter and voltmeter, there are a couple of things that you need to understand. So first, let's look at voltmeters. When you use a voltmeter, you're going to always hook it up in parallel. And in your lab manual, there's a diagram on this. So if I have a circuit and I want to know, hey, what is the voltage across this resistor? I will take my voltmeter and hook it up in parallel in that way. Now, in practice, what's that going to look like? Well, I'll have my power supply here, my terminals, I'll have my resistor. You're using these little boards with your resistor on them. And then your voltmeter will connect here in parallel with the resistor. So in practice, that's what it's going to look like, but this is the diagram that we will draw. You'll always hook it up in parallel. Also, you're going to hook it up so that it's red to red, black to black. In fact, if you're ever using your voltmeter and you're just not getting a reading, it's probably that you have it hooked up incorrectly. It can't measure a voltage, a negative voltage. It only measures positive voltages. So if we think about our power supply, this is the red side, this is the black side. Right? You have a red terminal here and a black terminal here. Now, it doesn't matter for the resistor how you put that in, but it does matter about the voltmeter. So I'm going to have the red side of my voltmeter always closest to the red side of the power supply, and the black side of my voltmeter always closest to the black side of the voltmeter, or the black side of the power supply. As I said again, if you ever have your voltmeter, it's just not getting a reading, or actually you can see where the needle's trying to go in the opposite direction. It's like twitching and trying to go into the negative direction. It probably means that you have the voltmeter hooked up incorrectly. That is, that you have red to black and black to red. The red terminal is always connected to the higher energy side, and the black terminal is always connected to the lower energy side. This is an electric field. It's energy. More about that in just a second. So for ammeters, they're going to look like this. So an ammeter will always be hooked up in series. So let's say that I have a circuit. In your lab manual, they give a parallel circuit. It doesn't really matter if it was parallel or series. In fact, I'm going to leave this off, this top part off, just to make this figure a little simpler. Now, if I want to measure, say, hey, what is the current in this circuit? The way that I'm going to do that is I'm going to take my ammeter and place it in series with that resistor. The way this will look in practice will be like this. I will have my power supply here. I'll have my resistor right here, and of course this is on our little wooden board that you use in lab. I'll show you another video about that later. And then I'll have my ammeter hooked up here. Your ammeter looks a lot like the voltmeter. Like it's on a metal stand, has a dial on it, but it measures current instead of voltage. So that's how you're going to hook it up. You'll hook it up in series. If you ever want to hook up an ammeter, you hook it up in series. Never hook it up in parallel. And you'll see why that is soon. Just a caution of warning, the ammeters are not as sensitive as the galvanometer, but they can be burnt up, that you can put too much current through them. So if you ever see your ammeter peg out its dial, that is that the dial goes all the way over to the right, then just remove it and then, reduce the power in your power supply, or probably you have your ammeter hooked up in parallel instead of in series. So be careful of that. Do not burn up our ammeters. For ammeters, current should flow from red to black. That is that I'm going to have my red here and my black here. This is assuming that we have conventional current. We'll talk about this in the class. Conventional current is not the actual flow of the current. Conventional current assumes that we have protons flowing. And the reason for this goes back to Benjamin Franklin. Benjamin Franklin thought that electricity was the flow of protons, not the flow of electrons. Later we learned that these charged positive particles are not the ones that are flowing through for current, that instead it's negative particles or conduction electrons. But nonetheless, we keep conventional current. Remember when we talked about the mountain? Whoop, I lost my pen there. When we talked about the mountain, that if this is the high potential and this is the low potential, positive particles tend to roll downhill, as you would expect them to. Negative particles do the opposite of what you would expect. That is, they move uphill. They move from low to high potential. But positive particles, or protons, move from high to low. So that is the direction then for conventional current. This is my high side of my battery. This is the low side of the battery. So if I have a proton right here, it's going to move in this direction. An electron will move the opposite direction. So I say that to say that we're going to have, this is our high side, that's the red side. This is our black side. The ammeter that's closest to the red side should be the red, and then closest to the black should be the black. So if I'm thinking about my current flowing through this circuit, it's going to flow then from red to black. You can also think of it in a similar way. Sorry, let me get rid of this. Think of it similarly as the voltmeters, that you have this red to red, black to black. But it's a lot better to think of it in terms of the current flowing. That current flows from red to black, from the high to the low. High potential to low potential. And that's what we will always set up our... let me pause here for a sec. We'll always set up our ammeter moving from red to black. Let's look at the components of the voltmeter and the ammeter. We'll look first at the components of the voltmeter. Voltmeter is pretty simple. So if I imagine my voltmeter is in this box. So this is the thing that you have in the lab. It's that metal frame with the dial on it. Within that metal frame, there are two parts. There's a galvanometer, and then there's a resistor. And they are connected in series in this way. So these would be the terminals, the red and the black terminals on that device that you would connect to whatever. This resistor, which is in series, we'll call it RS. R series is very big. It's very big and it's hooked up in series. So there's two very important ideas about this, that the resistor here is very big and it's also in series. The total resistance of this voltmeter then, the total resistance of the voltmeter will be equal to the resistance of the resistor in series plus the resistance of the galvanometer. But you know what? The resistance of this galvanometer is very, very small. So mostly the resistance of our voltmeter is this resistance in series. Okay. Um, One result of this is that when I hook up my resistor, my voltmeter rather, in parallel, I have a very big resistance right here. And remember how when I have current that comes here, then I have some current that goes here, and then I have other current that goes here. Now, I total, I'll call this I1, I'll call this IV, I total is equal to I shall call this I resistor plus the current going through the voltmeter. But because I have such a big resistance here, the current through that voltmeter is incredibly small, and the current through the resistor is most of the current. So our I total is mostly equal to I through the resistor. When you're using measuring devices, in general, you don't want those measuring devices to change the circuit. Let me repeat that. When you use measuring devices, in general, this is in general true anytime you're measuring some quantity, you don't want the measuring device to affect the quantity that you're trying to measure. So that's true here, that our voltmeter has a big resistance, and because it has a big resistance, it doesn't change the current that's flowing through the circuit. However, remember that resistors in parallel have the same voltage. That was one of our rules when we're talking about circuits, resistors in series and parallel. Resistors in parallel have the same voltage. So whatever voltage I have here, I have that same voltage here, which is what you want, right? You want to measure the voltage across this resistor. That's why you hook it up in parallel, so that it will have the same voltage as the resistor. Now, let's look at our ammeter. Our ammeter is a little bit different. Our ammeter consists of a galvanometer and a resistor. That resistor will be small, and it's in parallel. So if I imagine that this is my ammeter, this is the metal frame with the dial on it, it consists of two things. It consists of a galvanometer, and then connected to that galvanometer is what we call our shunt resistor. So actually, let me fix it. So I have a resistor here, and that resistor is called the shunt resistance. So R shunt. It's sort of a fun word to say. Try saying it right now. R shunt. 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 I sort of like to say it. You might not. But anyway, this shunt resistance, R shunt, has two things about it. It is in parallel with a galvanometer, and it's really, really small. In fact, it's basically just a wire. If you look on some of your ammeters, you can look in the back of the ammeter and you'll have a clear plastic case and you'll see a little wire, sort of looks like this. That's the shunt resistor. So when you get in the lab, take a look at the back of your ammeter and you'll see the shunt resistor. In fact, later we'll add another shunt resistor that will in fact just be a wire. So this shunt resistor is both in parallel, and it's very, very small. Now, because of that, think about this, that I want to know a current through a wire. I want to know what is this current equal to. Now, I don't want to affect my circuit in any way. I don't want to impact the current. So because this shunt resistor is really small, that's basically just a piece of wire, effectively, most of the current is going to go through this part. And then a tiny little bit of current is going to go through the galvanometer. So in that way, as far as the circuit thinks about it, well, circuits don't think, but if it did think, it would say, this person has added an ammeter to my circuit, but it looks like they've only added a piece of wire because most of the current is going through this wire. Okay, so let's look at two things that we can do to a voltmeter and an ammeter, and then we'll get to the more practical parts of this experiment. What you're going to be asked to do is to increase the range of a voltmeter and increase the range of an ammeter. In order to increase the range of a I'm sorry, hold on. Sorry, I jumped the gun there just a little bit. There are two other things that I wanted to say. I wanted to correct something in your lab manual, and I want to talk to you about hooking up that ammeter in series. So first of all, it says in the lab manual that the resistance of the ammeter is equal to the R shunt plus R of the galvanometer. That is a mistake. Of course you know that because they're hooked up in parallel. So really the resistance of the ammeter is equal to 1 over R shunt plus 1 over Rg. Now when you hook up resistors in parallel, like we're doing here, the shunt resistance and the galvanometer resistance, the equivalent resistance, which is Ra in this case, is always less than the smaller resistance. And which of these has the smaller resistance? Well, that's going to be the shunt resistor. So the ammeter has an equivalent resistance that's actually less than that of the wire. Because, you know, you can think about it that current comes along here, and it actually now has two paths that it can follow. One has a very small resistance, basically just a wire, that's the shunt resistor, and then the other has a slightly bigger resistor. The galvanometer actually has a pretty small resistance too, but the overall effect is that the equivalent resistance of the ammeter is very, very small. Now, how do you hook up an ammeter in a circuit? If I want to know the current through this resistor, how am I going to hook up an ammeter? I will hook it up in series. That's one of our basic ideas for ammeters, that we hook them up in series with the device that we want to measure. As I said, this has a very small resistance. So if I imagine the voltage here and the voltage here. Now if this circuit just looked like this, whatever the voltage here is, that's going to be the voltage here. So if this is, this would be VR. So I know in this circuit that V is equal to VR. Now let's think about this circuit when I add in the ammeter. I'll say this is VR, this is VA. I know in this circuit that V is equal to VA plus VR. That was one of our rules for resistors in series. The sum of the voltages is equal to V1 plus V2, or rather the source voltage is equal to V1 plus V2. That was one of our rules when we talked about resistors in series and parallel, and later we'll call this actually the loop rule. You can just sort of file that away for now. We'll use that a little bit later. Now remember, this has a very small resistance. And the current through both of these resistors is the same because resistors in series have the same current. That's another of our rules, right? That IR is equal to IA. But if one of them has a really small resistance, that means that VA is much, much smaller than VR. So if this number is much, much smaller than this number, then I can say that V is mostly equal to, very, very similar to VR. And in fact, we would say that V is equal to VR because the resistance of the ammeter is so incredibly small that VA is insignificant. Okay, so how do you increase the range of a voltmeter? You increase the range of a voltmeter by adding a resistor in series with the voltmeter. This resistor that you add, this is called a multiplier resistor. It's not nearly as fun to say as shunt resistor, but you can say it now if you want, multiplier resistance. We're going to call this RL. I don't know why L. I guess because multiplier has an L in it. Anyway, we call it RL. And what this does is it increases the overall resistance of the voltmeter. Because remember, the voltmeter is equal to the resistance of the galvanometer plus that resistance that is that in series with the galvanometer. But now we're adding another resistor in series with the galvanometer. Let's imagine that I have a voltmeter. And I know that the resistance of that voltmeter is equal to 5,000 ohms. And the full swing voltage is equal to 10 volts. Now, I didn't really understand this when I first heard it, so let me draw a picture. So this is the dial of our voltmeter. And the dial has a little needle on it, and then it has number 2, 3, and then goes on up to 10 volts. Full swing means when this thing is all the way over here, it reads 10 volts. That's what full swing means, that the dial or the needle on the voltmeter swings all the way to the right. So the full swing voltage is 10 volts. That means that in order for this to read full swing, then I know that the current through this thing has to be, well, I is V over R, or 10 over 5,000, or 0.0002 amps. Nope, I have too many zeros there. Whoops. So 0.002 amps. Now, if you want to increase the range of your voltmeter, this is what you do. You take your voltmeter and you put it in series with a resistor. Now let's think about this. So let's say that I add a multiplier resistance equal to 5,000 volts. And then I now have, I know that the resistance of my voltmeter is also 5,000 volts. If I have a power supply that has 10 volts here, then I know that the potential across each of these devices is going to be 5 volts and 5 volts. So even though I have 10 volts in the circuit, my voltmeter is only reading 5 volts. So what happens if instead of reading 5 volts, I now have my voltmeter so that it reads 10 volts? That is, if I set up this circuit so that this is 10 volts, what does that tell me about this voltage? Well, in this case, both of these resistors are the same, so I know that the voltage here has to be the same as the voltage here, and so this voltage has to be 10 plus 10, or 20 volts. So now I've multiplied my reading on the voltmeter. Instead of reading here 10 volts, when the needle is in full swing, it's actually reading 20 volts because I've added this multiplier resistance. That's a pretty powerful tool. Later, those of you that are chem majors, when you take instrumental, you will work with Dr. Wayment or Dr. Marlowe doing some more advanced circuits, and you'll build what is called a voltage divider. It's effectively this, that I have two components that split up a voltage into two separate pieces, and then it allows you to read a bigger voltage. So I can write this out in equation form. It's in your lab manual, but my new full swing voltage is equal to my current. That's the current on the ammeter that will cause it to go into full swing. And that doesn't change. It's 0.002 because you can't change the resistance of the actual voltmeter, times RV plus RL. That will be equal to 0.002 times my new resistance, or 10,000 ohms. That's fun to say too. Ohm. And then that's going to be 20 volts. That is my new multiplied full swing voltage. Okay, let's look at increasing the range of an ammeter. You've hung on now, so let's keep on hanging on. This is probably the most difficult to understand. So listen closely. A user can increase the range by adding a shunt resistor. And you're going to add that shunt resistor in two ways. You're going to add it so that it's in parallel, and you're going to add a shunt resistor that is really small. So you hook up your shunt resistor in parallel, and you hook up a resistor that's very small. Let's imagine that you have an ammeter that has a full swing current of 10 amps. That is, if I have 10 amps current coming through here, then this will read a full swing current of 10 amps. Okay? So I'm going to now take that and I'm going to add a shunt resistor, and it'll look like this. I have my ammeter right here. I'm going to add my shunt resistor. Remember, is it big or small? It's really small. It's basically just a piece of wire. In fact, you'll see that in the lab that we'll add a piece of wire. So I'll write that over here. It's just a wire. It's a very tiny resistance. This is our R shunt. I'm going to call it RS. Now imagine that I have 10 amps coming in here. If I add a shunt resistor, some of that current will be diverted. Remember, one of our rules for resistors in parallel is that I is equal to I1 plus I2 plus however many branches we have in that parallel circuit. So this current is being split up into different parts. Now, say that I have 9 amps going here. That means that I just have 1 amp going here. So whereas before, the needle on this thing was way over here at 10 amps, now it's way over here at 1 amp. So I only have 1 amp reading on the ammeter, even though I really have 10 amps in the circuit. So this has given me a 10-fold multiplication. That I have a real current of 10 amps, but I'm only reading 1 amp on the ammeter because I've diverted some of that current away from the ammeter when I added this shunt resistor. A 10-fold multiplication. Now, what if I had a reading on the ammeter that was equal to 10 amps? That would mean that I would have a current over here of 100 amps if I have a 10-fold multiplication. Okay? This is the new full-scale current reading, which I'm going to call IFS prime. Now, if we think about this, I'm going to redraw this circuit. We can write an equation that describes this. I'm going to call this IFS prime. This will be IFS. That's the full swing current that goes through the ammeter. The current through the ammeter that causes it to be full swing. And then this is going to be IFS prime minus IFS. Because these two components, the resistor and the ammeter, are in parallel, I can say that the voltages across them are identical. That is to say that IFS times the resistance of my ammeter is equal to IFS prime minus IFS times the resistance of the shunt. All I've said there is that the voltage here is equal to the voltage here. This is IFS-RA. That's the voltage across the ammeter. This is IFS prime minus IFS, which is that current from this junction of the circuit, times the resistance of this shunt resistor. That'll be an important equation. We'll use it as we try to increase the range of an ammeter and calculate what the multiplication factor is.